Welcome to the Automate workshop. Hi, I'm David. In this fundamentals module, we'll be examining the low and high pressure fuel system of the common rail diesel. The common rail diesel fuel delivery system is very different from the old mechanical system. We use much higher pressures. This gives us better atomisation of the fuel, lowering emissions and giving us more power. Electronic control combined with multiple injection events means that we use less fuel, so we get better fuel economy. I'll go through the components and their operation and show you their location. So let's explore the fuel system of the common rail diesel engine. Here is a typical list of inputs or signals from a CRD. These will vary slightly from engine to engine. The ECM processes this information and provides these controls or outputs. Again, these may vary slightly from engine to engine. There will also be serial data exchange between the ECM and other control units via the bus. The signals that apply to the fuel system are rail pressure sensor, fuel temperature sensor, water in fuel sensor, and fuel level sensor. And on the control side, there is the injectors, metering or suction control valve, rail pressure control valve, and the fuel pump control. The fuel tank stores the fuel for the system. There is no vapour line, just a supply and return line. The fuel pump and fuel sender in this vehicle is accessed through this opening. There is no large vapour space that would be found on a petrol fuel tank. The reason for this is the flash point of diesel. The flash point of a liquid is the temperature it has to reach to give off flammable vapours, and in Australia this should be a minimum of 61.5 degrees Celsius for diesel. This should not be confused with the self-ignition temperature. This is when the fuel will ignite without an external source and is around 210 degrees Celsius. The schematics we'll be using are typical for most systems. Always check the schematic relevant to your vehicle. Most vehicles will have an electric pump in the tank. This schematic is typical of an electric fuel pump circuit. The engine control module operates a high side driver to turn on the relay. The relay then provides B+ to the fuel pump. From the pump, the fuel will travel to the filter. These will be in various locations. On this vehicle, it's underneath the floor. On others, it could be in the engine bay. This filter also has a hand priming pump. Some are even mounted on the engine itself. There is usually a water and fuel sensor in the filter. This will illuminate a warning in the instrument cluster when the water reaches a predetermined level. Water in the fuel can cause corrosion. Many parts of the high pressure pump and injectors have extremely fine clearances. Any corrosion here could be disastrous. Bacteria and fungus can live in the water, feeding on the hydrocarbons of the fuel. Clean, good quality fuel is essential for common rail diesel engines. On this schematic, the water in fuel sensor has an ignition supply and a ground. When the water reaches a predetermined level, a ground is sent to the ECM from a low side driver. The fuel temperature sensor is a 2-wire sensor with a signal wire going to a pull-up circuit in the control module. The fuel heater relay is operated by a low side driver in the module. The fuel heater will only be required in very cold climates to help make starting easier. In most areas of Australia, it will not be needed. Remember, pressure in these systems could be as high as 2,500 bar, so safety is of key importance when working on the high pressure side of these systems. The high pressure can be varied either using a 1-point or 2-point control. In a 1-point control system, the fuel pressure will be controlled either at the pump or at the fuel rail. The pump control will be done by a metering valve or a suction control valve, and at the rail by a rail pressure control valve. At the pump, the valve will control the amount of fuel going into the pumping chambers, thus varying the rail pressure. The rail pressure control valve will vary the amount of fuel that is returned to the tank, thus controlling the rail pressure. A two-point control system uses both these methods to vary the fuel pressure. You may be wondering why it's necessary to vary the fuel pressure. Why not just leave it at its maximum at all times? One of the reasons is fuel economy. It requires more power to create more pressure, and more power means more fuel. More importantly is the time required to inject the fuel. If the pressure was at its maximum and the engine was idling, the injector wouldn't be open for very long to deliver the amount of fuel required. This would be hard to control. By reducing the pressure at lower engine speeds, it gives us a longer injection duration, and this is much easier to control. Some CRD engines may have a pressure limiting valve in the fuel rail. This is a simple spring-loaded valve. When the valve opens, the excess fuel will be returned to the tank. This will prevent excess pressure within the fuel rail if the monitoring system fails. The high-pressure fuel is supplied to the fuel rail, and because of its design, will help reduce pressure pulsations from the pump. The fuel is now stored, ready to be used by the injectors. The high-pressure pipes into and out of the fuel rail may be of the single-use type. This means if they're removed, they must be replaced. Always refer to the manufacturer's information. Failure to do so could cause a fuel leakage and a possible fire. Also remember, when working on any component from the high pressure pump onwards, you may be exposed to fuel under high pressure. Always wear your safety glasses and gloves. The fuel injectors will receive a control from the ECM, which will determine when and how much fuel needs to be injected. These injectors operate rapidly, giving very fine control over the injection quantity. Because they are electrically controlled, it is possible to have multiple injection events, rather than just one single event. There are two types of CRD injectors, solenoid and piezoelectric. Both types use fuel pressure to open and close the injector. The solenoid injector consists of an electromagnetic coil, a two-way valve and return spring, a command piston, and a needle and its return spring. When the solenoid is energised, the two-way valve is pulled up against spring pressure. This will open a passage above the command piston, causing a reduction of pressure as the fuel escapes out the fuel return. The pressure acting on the needle is now greater than the spring pressure and the fuel pressure acting on the command piston. This will allow the needle and command piston to lift. The fuel can now flow past the needle and out of the nozzle holes. To close the injector, the solenoid is de-energised. The two-way valve will now close. Fuel pressure will now build up above the command piston. This force, combined with the force of the needle return spring, will cause the needle to reseat, blocking the flow of fuel. The piezoelectric injector also comprises a control valve and return spring and a needle with a return spring, with the addition of a piezoelectric element which contains many hundreds of piezoelectric discs. A high voltage and current is required to cause the piezoelectric stack to expand or contract. The valve is operated by the piezoelectric stack, allowing the fuel above the needle out of the return line. This reduction in pressure allows the needle to lift against the return spring force. Fuel can now flow out of the nozzle holes. When the opposite current is applied to the stack, the control valve will be closed. This will allow pressure to build up above the needle, and this combined with the return spring force will reseat the needle. The major advantage of piezoelectric injectors is their speed of operation and the repeatability of their movement. The movement of the piezoelectric stack is almost instantaneous. This reaction speed allows even more precise control and a greater number of injection pulses. A fuel return line is connected to the injectors, rail pressure control valve, pressure limiter, and the high pressure pump. On this vehicle, the return fuel goes through a fuel cooler before going to the tank. As the fuel goes through the injectors, it will increase in temperature. This is caused by the fuel pressure and the temperature of the engine. An increase in diesel fuel temperature will cause a lack of power, so a fuel cooler may be employed to counteract this temperature increase. So that's our in-depth look at the common rail diesel fuel system. Remember, this is just one module in a series that's taking a closer look at CRDs. Always refer to the manufacturer's specification when performing any work on the fuel system. Don't reuse any component made for one use only. And work safe. Always use the correct PPE. When replacing a component in the fuel system, always make sure that the failure was not caused by the fuel itself. Many problems can be attributed to poor fuel, and if this is not rectified, the system will only fail again. And always remember, training is the key to your success. Bye for now.